So our next speaker is Sho Yaida, and today he will talk about non-Gaussian processes and neural networks and finite width. Please, Sho.
Thank you. Thank you for the introduction. So the story of my paper begins with this conjecture made by Mehra and Schwab in 2014, which states that the neural network inference is equal to renormalization group flow. So what does that mean? So like in a typical inference task, neural network takes the input data, like such as a spectral cow, and then pass on to the layers and then get the output, which basically predicts that which picture this is. In this case, it's a cow. And the folklore states that the first layer detects the edges in the picture, and then the next layer assemble this information into like a nose and like ears and so on, and then assemble this information again to make a prediction like a cow or cat. So like in doing this, like neural network inference is like assumed to like be doing the following, like wash away irrelevant details and extract relevant features, such as a prediction like a cow. So this similar things happen for renormalization group flow in connecting microscopic world to the macroscopic world. So you start with a microscopic theory, like string theory, and then you zoom out and you get the quantum electrodynamics. And then you zoom out, you get the molecular scale, and then you zoom out again, and you get to the everyday life scale. And the renormalization group flow basically provides you a systematic way to carry out this procedure, like washing away irrelevant details and extract relevant features. So seeing both sides of the equation, you might naturally conjecture that the neural network inference is equal to renormalization group flow. But the question is, like, can we make this actually precise for the real neural network that people use in practice? And in addition, can we learn anything practically useful from doing this? And the answer is yes and yes. And my MSML paper basically addressed this first question, which is, can we make this relation between the inference and RG flow precise? Okay. So when you have a neural network, you might think that keeping track of what each neuron is doing would be pretty hard. But physicists come along and say, if you look at the lots of neurons and then ask about the statistical distribution of these like lots of neurons, say infinity, then like things should simplify. In particular, if you take an infinite number of neurons, then that's a regime where typically things are controlled by large numbers, say like everything's Gaussian. And not only that, you can kind of systematically back away from the ideal limit of infinite neurons and using the perturbation theory. So that's what we want to do. Okay. So this first limit of going to the infinity is taken by Radford Neal in 1996. And recently revived by Google Brain Group by Jaifeng Li, Yasman Bari, et al. In this IQF paper. And basically what you do is that you keep the input dimension and output dimension fixed, and then take the number of neurons in a hidden layer to infinity. And then you find, as predicted, that everything is Gaussian, and then you can do everything you want in this regime. But you might say that this is too wide, too unrealistic, because like no neural network have infinite neurons. So how can we systematically back away from this ideal limit to make keep touch with the reality? So like that's what we did. What I did in my paper, which is basically use a perturbation theory to include the correction that comes from the finite width, like 1/n corrections. And there's all the traditional physicist toolbox going back, like large N expansion and so on. So you can employ that technology here to actually like see like how this finite width would correct the behavior neural network. And more precisely, what I've done is that you can try to keep track of the statistical distribution of neural activation at initialization, going from lower layer at first layer to the last layers gradually. And basically what you do is that the coarse graining technique you see in the RG flow, which is like basically integrate out the microscopic variables and then like pass on to the more macroscopic variables. And you can recursively keep track of distribution of neural activations from lower to higher layer. And there's even some equations, like K is kernel, so it's kind of recursive equation that you expect from RG intuition. And D is a 4-point connective function, which basically captures the non-Gaussianity of the distribution of neural activations. And S is a self-energy correction to the kernel coming from the finite width. Okay, so as you do this coarse graining procedure and then keep track of pre-activation distribution all the way up to the top output layer, then once you have this prior distribution of pre-activation at top layer, then you can actually use this to do the Bayesian inference. And this is basically all you need to make a prediction out of neural network. Okay, so in this Bayesian framework, like you can basically, this neural network inference is being enabled by coarse graining and passing on the distribution of information from first layer to second and third to the last, just as you do in a renormalization loop flow where you go from microscopic scale to the macroscopic scale, keeping track of effective Hamiltonian governing the probability distribution of random variables. And this is done for real finite width network. So that was my paper, and then you can look at the details in my paper. But in the last 9 months, we made more progress. So I want to use last some minutes to say something about that. So in joint work with Boris Han and Dan Robert addresses, can we run anything practically useful? So just to summarize what I've done, we take an infinite risk limit and then back away from that limit to include the finite risk corrections. And you use law of large number and the perturbation theory. And you basically look for the simplification that comes from the wideness of the network. But can we can also take not only the wide, but then also like deep network. So and then look for simplification that comes, further simplification that comes when your network becomes really deep. And in this way, we're basically carrying our theory for deep learning, employing the simplification only when depth is large. So this is joint work with Boris Han and Dan Robert, and we worked like pretty hard over the last 9 months. And we could have published like many conference paper, but we thought that it's better to write a complete and pedagogical monograph. So please look forward to that. And here's the last slide with a practical takeaway. But I will just show this slide, and I'm happy to take some questions if there's any.
You have time to actually go over the slides, so
okay, great.
Why don't you do that?
Yeah, okay. So basically, this takeaway can be read off by like trying to avoid the exploding and vanishing gradient program. So we can say, for example, some activation function should never be used for deep learning, like sigmoid, soft plus, and so on should never be used, and then sigmoid should be replaced by tanh, for example. And people have noticed like empirically, but then we can now see why people had trouble with sigmoid. And once you have some like good activation function, then we can say like how to initialize weights and biases for the good training. So like if you do this for ReLU network, then you recover the famous Chi-mean initialization. And then for tanh activation function, you have like 1√2 of that or the half the variance. And so any activation you give us, we can say that, okay, this should or should not be used for deep learning. And then we can tell you how to initialize weights and biases. And on top of that, we can also say like what kind of initial learning rate should be used. Like we can give a rough estimate, like how it should scale with depth, for example. And also for tanh, we can say like more, we can actually suggest novel initialization or initial learning rate scheme where like you can make the learning rate layer dependent to further make the training better. And then finally, we can say something about the architecture. And one thing that comes up again and again in our calculation is that the depth over width should be not too large. So the aspect ratio should be such that the network should be wider than deeper. And also it should be pretty uniform. It shouldn't be like getting wider or shallow, narrower. It should be pretty uniform. So we hope to push this a little bit farther, but that's the direction we're going.
So the next question is for Sho Yaida. Are there any results for trained networks? So I suppose that's like after the training.
Yes, so like we do have some results, which is like in joint work with Boris and Dan. And basically you can actually try to say something about the generalization gap or the robustness when you have a training set and input set nearby to each other. So that's one thing. Like we can actually say something about how the generalization gap depends on hyperparameters and so on in a large width network.
Okay, and another question is, sometimes there is a conservation rule related with partition functions for RG flow in physics. Is there anything similar in your setup?
Not that I know of. There's actually some rule that kind of says the consistency condition for like when you kind of integrate out some inputs, but not any conservation law that I see.
Okay, maybe another short question. So does the finite width correction induce a process with heavy tails?
So the answer is no. So like when you start with the weights and biases, which is assumed to be Gaussian, then you kind of get the Gaussian plus some small corrections. So it's not heavy tail, but then part of it is controlled in one over width.